So this one's set up a little bit differently. So this one's a little tricky, and it's kind of exactly the kind of question I like to put on tests. Just saying. So since we're dealing with calculating heat, what equation are we going to be using? We're going to be calculating Q. So what's Q equal to?
Specific heat.
Mm-hmm. Yeah, so our specific heat times?
The mass.
Yep.
Times the change in temperature.
Times delta T, that's right. Exactly. So let's look at what the information we actually have. So got a mass here. So I've got 275 grams of nickel. I've got an initial temperature of 100 degrees C. And I've got a mass of water as well. You can see I've got a volume, but we pretty much know what the mass of that is, right? How much, so as far as water goes, what would be our mass of water?
100 milliliters.
That's our volume. What's our mass?
Was it that 4.184?
Nope.
No, that's specific heat.
What's the mass of 1 milliliter of water? What's the density of water? That'll help us answer that question.
1 gram per milliliter.
Right, it's 1 gram per milliliter. That's basically where we get the gram from. It's the mass of 1 milliliter of water. So if I have 100 milliliters of water, how many grams do I have? If it's 1 gram per milliliter,
100.
100 grams, right? Yeah. So 100 grams. And my initial temperature of water is 22. So basically what we're asked to figure out here is, since the heat is going to be transferred from the nickel to the water, what happens when all the heat has been transferred from the nickel to the water? What's going to be the temperature of both the nickel and the water? Are they going to be the same, or are they going to be different?
The nickel is going to have a lower temperature.
Lower temperature than the water?
Once it's inside the water.
Well, the temperature will start dropping, yes. But when they equilibrate, when all the heat has been moved from the nickel to the water, what can we say about both the temperature of the nickel and the water?
They'll be equivalent?
They'll be the same, exactly. As we noticed that when we did the experiment, right? We put our metal in. The temperature of the metal dropped pretty quickly, and the temperature of the water slowly rose. But then when they got to the same temperature, we stopped the experiment and noted that temperature, which is exactly what you would have done in the lab as well. Because when the temperature is the same, that means that all the heat from the nickel has been transferred to the water. And then they'd both start dropping because they'd both start losing whatever heat they had left to the surroundings. We're not really interested in that. We just want to see how much heat goes from the nickel to the water. So basically, we don't know what the final temperature is going to be. That's the question. But we do know that the final temperature is going to be the same for both the nickel and the water. It's going to be the same. So basically what we're going to do is set up an equation where we can solve for the final temperature. So what do we know about Q nickel and Q water? At the end of the experiment,
They're the same number, but one is opposite. One is
right?
negative, one is
They're the
positive.
same. They're the same absolute value, but reversed, because Q. Let me just erase some. Let me just clear this up because we want to draw on this. So at the end of it, we're going to know that Q nickel is going to equal the specific heat of nickel times the mass of nickel, which is 275 grams, times the change in temperature. And that's going to be 100 degrees C minus the final temperature, right? That's so far so good?
How do we find the final temperature?
That's what we're going to do. We're going to figure it out. We're going to use math. So that's also going to equal minus Q water, right? One is the opposite of the other. And that's going to equal the specific heat of the water times 100 grams times, and now this is where the tricky part comes in. That is going to be the final temperature minus 22 degrees. Let me move this out of the way so I can. Minus 22. So basically what we're dealing with, so our CP, our specific heat of the nickel, is 0.444 joules per gram Kelvin, or degrees C, makes no difference, times 275 grams times 100 C minus TF equals, so minus that is going to equal CP of water. What's the specific heat of water?
Zero 0.4184 joules.
Multiply that by 10. It's 4.184. Remember, water's specific heat is really high. That's much, like it's almost 10 times as much as nickel. So joules per gram
186
Kelvin times 100 grams times TF minus 22 degrees. So basically what we're going to do is just multiply all these things together and then see what we can cancel. Okay, so I've got grams here, and I've got temperature here, so I can cancel that. I've got grams here, and I've got temperature in here, so I can cancel that. Basically what I'll come up with is, so 0.444 times 275 times 100 minus TF equals 4.184 joules. This should be joules here. Times 100 multiplied by TF minus 22. And basically we just multiply all these things together and then work out what TF is going to be. So let me move this up here. Everyone following along so far? Is this it's not making any sense to anybody? I'm just doing just basic math, moving these things around. It's just algebra. Like I said, if you have trouble with algebra, you're going to have trouble with this, with with gas laws or with thermo. But if you're good with algebra, it won't be a problem. So you see, basically, I've just taken the expression and expanded it. So is anyone understanding what's going on so far? Should I start over?
No, I understand.
Should we? So basically, I'm just taking, so this is our, oops. There's our specific heat. There's our mass. There's our temperature for the nickel. Now, on the other side, here's our specific heat for water, the mass of the water, and the temperature of the water, the delta T. This is the delta T for nickel, and this is the delta T for water. So they're going to be different. The delta T for, actually, I did this wrong. Damn it. Yeah, it's TF. Shit. This is, I've already made a mistake. See, if you don't do these for a while, you make a mistake. So instead of minus, it should be TF minus 100. TF minus 100. Because remember, we always take, the delta T is always the final temperature minus the initial temperature. So I screwed that up. So hopefully this will make more sense now. Okay, TF minus 100. So that's the final temperature for the nickel. This is the final temperature for the water. So for the nickel, it's going to be negative. For the water, it's going to be positive. Okay? So let's take this whole thing and move it up to the top. So now we can start punching in our numbers. So 0.444 times 275. That's 122.1. So this is 122.1. And over here is 418.4. That's just these two multiplied together and these two multiplied together. Does that make sense to everybody so far?
Professor, in the beginning, you put negative, but it will not affect in our calculation, correct?
Yeah, one side's going to be negative, one side's going to be positive.
Yeah. And when it's negative, that means it's lose temperature.
Yes.
Okay.
The nickel side's negative because the delta T for nickel is going to be negative. So when you multiply the two negatives together, you'll get a positive. So that's actually going to be negative 122 on that side. This is going to be plus 418 on this side. So we just put them all together. So minus 122.1 times TF plus minus 122 times minus 100. So that's going to be plus 12210. So see, we just cross multiply this minus 122.1 multiplied by TF, and then we also multiply it by minus 100. That's going to be equal to 418.4 TF minus 418.4 times 22. So minus 9,200 and, whoop, sorry. Can't look away and draw at the same time. 9,204.8. Okay? So this is degrees, and this is degrees as well, because these are temperatures, right? Temperature here, temperature here. So far, so good?
Professor, how you get 1 to 210 temperature?
So down at the bottom, I've multiplied the specific heat of nickel times the mass of the nickel. That gives us minus 122.1. And then I cross multiply my 122.1 times everything that's inside the brackets. And inside the brackets are the final temperature minus 100. So 122.1 times the final temperature, and then minus 122.1 times minus 100. And that's this.
Okay.
Okay?
Mhm.
I could start from the beginning if that would make more sense to people. Should I just start over? There's a lot of math here. All right, I'm just going to start over. Okay, so what we want to do is use the fact that minus Q nickel is going to equal Q water, right? All the heat that's lost by the nickel is going to go into the water. So this is just the basic assumption we make with any calorimetry problem. Then it's just a matter of writing out what is minus Q nickel equal to. Well, minus Q nickel is minus the specific heat, which is 0.444 joules per gram per degree. I'm just going to change Kelvin to degrees C because that's what we're dealing with here. Multiplied by the mass, which is 275 grams, times delta T. So remember, Q is Cp times mass times delta T. And our delta T for the nickel is, and the delta T for anything is always going to be the difference between the initial temperature and the final temperature, right? And the initial temperature is 100. And the final temperature, we don't know what it is. So this is what, oh God, I did it again. I keep doing that. Final temperature minus the initial temperature. I keep doing that. No wonder you're confused. Is final minus 100 degrees. Yeah, final minus initial. Keep making that mistake. Don't make that mistake. So that's going to be Q nickel. Now Q water is going to be 4.184 joules per gram per degree C times the mass of the water, which is 100, times delta T for the water. Now delta T for the water is going to be whatever the final temperature is minus its initial temperature, which is 22. So these two things equal each other. So are we agreed on that? So this expression up here is going to equal this expression down here. So far, so good for everybody? Does that make sense?
Yes.
Yeah, minus Q nickel equals Q water. That's how it has to be. So now it's just a matter of multiplying everything in here and multiplying everything in there because they equal each other. And then once we have numbers on both sides of the equal sign, then we can start moving things around and solving for TF. So the bottom one is going to be minus 0.444 times 275. Actually, let's just do the math here. So 0.444 times 275. So that was 122. So minus 122.1. That is these two numbers here times TF minus 100 degrees. That is going to be equal to
It's 122.2.
0.2. It is?
Oh, no, sorry, it's 122.1.
Oh, sorry. Yeah. I'm just looking at my calculator. It's just definitely, I know I'm a little flustered today, but I didn't think I got that wrong. So then the water side is going to be 4.184 times 100. So that's 418.4 times TF minus 22 degrees. So basically now that we have this, we can solve for TF, okay? Because that's what the question is. Can you solve for the final temperature? So let me erase all this stuff.
So did the joules go away?
Basically, yeah, I mean, so yeah, I mean, basically we have joules on one side and joules on the other. So 122 now is basically the units of this are joules per degree C. That's what these are. This one and this one, because we've multiplied by grams, so we canceled the grams. I basically I just left out the units. I say that's a bad thing to do. I'm a bad person for doing that. But yeah, so the units are joules per degree C at this point. So now, yeah, I just sort of just left them out because it made a difficult question even more difficult. But I can put them back in. So now I have minus 122.1 TFs plus, so minus 122.1 times minus 100. So that is 122. Okay, so I multiplied this by this, and then I also multiplied this by that. So you see how you can do that, right? I'm multiplying a number by something in brackets, so I multiply that number by everything that's in the brackets. So that on the other side, I've got 418.4 TFs plus, now we have a minus number here. So that's going to be minus 418.4 times 22. So 9,204.8. So now we just move all the numbers to one side and all the TFs to the other side, and then we should be able to solve for TF.
But it was minus 920.
So what I'll do is I'll move this TF over here, and I'll move.
Professor, the other side should be negative.
It is.
Negative 902.04.
It is.
Oh, okay.
Yeah. So I'll move the TFs to the left and I'll move the numbers to the right. So I'll move these numbers over here. So what should I get on the left side?
Negative 540.5
Yeah.
TF.
So negative 540.5. Oh man, I can't even, definitely need a day off. So 540.5 TFs equal what? What do they equal?
Negative 21414.80 Celsius.
Negative 21414.8, right? Degrees. So let's divide both sides by negative 540.5. And what do we get?
39.620.
Minus 450.5 divided by negative 450.5. So TF equals what?
39.620 joules over minute.
0.62 degrees. So we probably would use 3 significant digits because there's 3 here, there's 3 here. So I'll probably just leave it at 39.6. Then what you can do is check, make sure that that's right. Go back and plug 39.6 degrees into the equation. So the delta T for nickel should be 100 minus 39.6. Or damn it, I'm still doing it wrong. I don't know why I'm stuck on doing that. So delta T for the nickel should be 39.6 minus 100. And delta T for the water should be 39.6 degrees minus 22. So this one will be 17.6 positive, and the other one will be minus 60.4 degrees. So plug that number into the nickel side, plug that number into the water side, and see if it all equals out. Okay? That's a long, long question with lots and lots of math in it. So yeah, expect to see a question like that on a test coming to you soon. Because basically, yeah, it just takes all the information we've learned so far, but then puts it in a slightly different, puts a spin on it, so that we have to do algebra to solve for the final temperature. But it's using the same equations that we should be familiar with by now. It's just using the equation for Q. And presume that you don't screw up like I always do and put the initial temperature as the final temperature for nickel, which I keep doing. You should be okay. So yeah, leave yourself a lot of room to do this one.
The answer would just be 17.
So did anyone plug the numbers in? Did it come out right? Let's do that. It's a good way to check our work. All right, erase everything. Okay, so Q nickel would be minus 0.444 joules per gram times 275 grams times negative 66.4 degrees. So 0.444 times 275 times 66.4. So the nickel should have lost 8,107 joules. And let's look at the water. So the water is 4.184 times 100 times 17.6. Hopefully we'll get the same thing. Did I do that right? 39.6 minus 22. I'm getting the same number. Hmm.
Isn't it supposed to be negative 7374.84?
Sorry, what was that? I couldn't hear that. Did I do it? Did I make it? I made the
Yeah,
calculation error.
it's supposed to be negative 60.4 for the delta T.
Oh, not 66. It's supposed to be 60.
Yeah.
That's the problem. Yeah, because I made a. I figured there was something. Yeah, because they scribbled the other one. You're right. That should be 60. Yeah, thanks. 60. Okay. Now I think we're in business. Times 275. Right. So 73.75 joules. And yeah, 73.64. Yeah, so it's pretty close. Yes, you may not get it like exactly because since we rounded to 3 digits, it's not going to be exactly the same. If our temperature was like 4 or 5 digits, it'd be exactly the same. But this is pretty close. So 73.75 joules versus 73.64 joules. That's close enough. So when you do this sort of problem, yeah, you're not going to get it exactly because of the rounding. Because your answer is going to have 4 or 5 digits in it. And the temperature you're plugging in only has 3. Well, that was nice and confusing. Who wants to, what one would you like to do next since we thoroughly understand that question?
Professor, I have a question.
Yeah.
From earlier, the numbers 540.5, how did you get those?
540.5. Oh, yeah, basically what we did is we took the specific heat of the nickel, so 0.444. So I'm just going to leave the units out, and then we multiplied that by 275. So this is the specific heat, and that is the mass, right? And we multiplied that by 100 minus. Damn it! I keep doing that. Why do I keep doing that? TF minus 100. I just expand it out. So this number becomes what, 100, that's 121.1 times both things that are in here. So I'm multiplying by both things. So I want to multiply that by TF and multiply that by minus 100. So that's where the two numbers come from. Then the same thing on the other side, but the other side is water. So there's our specific heat of water, and then there's our mass. And then we multiply that by the change in temperature. And this time it's TF minus 22. So just like when you're doing algebra, you multiply everything on this side by everything on that side. And there's two things inside the bracket, so we need to multiply that by both of them.
Oh, okay. I understood. Thank you.
Okay, yeah. It's It's probably your math skills may be a little rusty on this sort of thing. This is a good time to shake the rust off. Yeah, because unfortunately, yeah, we need to do a lot of algebra in chemistry because there's so many equations. And when we're solving for like one thing, basically that just means moving all the other units around until we're solving for the one thing we want. And in this instance, all we want is that. So we don't know, we know that delta T is going to be different on one side than the other, but the final temperature is going to be the same. So we can solve for that. Okay? We can always come back. We can always do another one of these at the end.
Can we do number 3?
Sure. Ooh, thermite. Anyone ever seen thermite? It's really cool to watch. Like Mythbusters, they use thermite a lot. Who's seen Mythbusters? Nobody? Nobody's seen Mythbusters? Oh my God. Such a great show, and a Bay Area show on top of that. So this is an extremely exothermic reaction. So you get yourself some iron oxide. So here's our iron oxide. And basically what you do is you just add powdered aluminum to it. So you just get some finely powdered aluminum, which by itself is dangerous because aluminum will burn. Like, anyone seen magnesium burn? Like a magnesium ribbon burn? It burns super, super hot and super, super fast. Aluminum does the same thing. So in this instance, aluminum will become oxidized. Aluminum will become oxidized, and basically the oxygen will move from the iron over to the aluminum. And in doing so, releases a tremendous amount of heat, okay? So basically we have 2 moles of aluminum reacts with 1 mole of iron 3 oxide. And then you get this intense amount of heat released. And then you're left with solid iron. And now aluminum is oxidized rather than the iron. So remember, when you have delta H, it's per mole of this reaction. So what we're looking for basically is either per mole of iron oxide or per mole of aluminum oxide. That's what we're looking for. So delta H basically equals, this is how much heat is released when 1 mole of iron oxide gets reduced from iron oxide to iron. So if 725 kilojoules of heat are released, basically how much iron did we start with? So delta H equals minus 850 kilojoules, basically per mole of Fe2O3. Now we have 725 kilojoules. So for every 1 mole of iron, actually I should flip those upside down. So for every 1 mole of iron oxide is equivalent to 850 kilojoules. Now we've got less than that. So we have 725 kilojoules of heat. So remember, you can treat this just like a product, because this is an exothermic reaction. We have 3 products basically. One product is the solid iron, one product is the aluminum oxide, and the third product is the heat that's released, okay? So when I multiply my kilojoules will cancel, and I'm left with moles of Fe2O3. So how many moles of Fe2O3 did I start with, basically?
One.
Nope. If I had 1 mole of Fe2O3, I would have released 850 kilojoules of heat, but I didn't. I only released 725. So how many moles of Fe2O3 did I start with? Just do the equation.
0.8529.
Yeah, 0.85. Oh, man, I can't look away and draw at the same time.
Negative?
No, they're both negative. If 725 kilojoules of heat are released, that's negative. So, and anyway, we can't have negative moles of anything. So 0.8529 moles of Fe2O3. So now we just go back to the balanced equation. If I have 0.29 moles of Fe2O3, that's how much I started with. What's the relationship between moles of iron and moles of iron oxide? From my balanced equation, what's the...
Over 1.
So there's 2 over 1, right. There's 2 moles of iron for every 1 mole of Fe2O3. Then I'm left with moles of iron, but I want grams, right? It says what mass of iron. So again, so I've got moles. I want to get rid of moles, so I put moles on the bottom. And I put grams, which I want on the top. So what am I going to put for grams here?
$55.845 grams
Yeah, but what is that?
of Fe, molar mass of Fe.
Molar mass of iron, right. So let's say it's 55.
0.845.
845. Okay. Yeah, so now we just multiply 0.829 times 2 times 55.845. So what's our final answer?
$95.265 grams of Fe.
95.265 grams. Right. So how many significant digits should I have?
Three significant digits.
How many significant digits?
3.
3, right, 3, because the heat is 725. So I would change that to 95.3 grams. And then just have a look and see if that makes sense. So if 1 mole is 55, 2 moles would be 110. So then I look and see, well, but I have less than 850. So yeah, so it should be less than 110, but more than 55. So it should be somewhere in between 1 and 2 moles. So that looks to be about right. Yeah, so in this instance, yeah, you just treat heat as a product. And you didn't actually have to go through all of the iron oxide. You could have just said, for every 850 kilojoules, I make 2 moles of iron. You could have done it that way as well and skipped a step. That's fine. And then gone right to moles of iron and then converted moles of iron to grams. So you need 2 things. You need to know You need to realize what delta H basically means the amount of heat for this reaction in those exact ratios. And then the other thing, you need to make sure your equation is balanced. So that's critical. I don't think I checked. Yes, it is balanced. But yeah, check on a test. I may be very mean and not give you a balanced equation. Make sure you double check and make sure that it is, okay? I've been known to do mean things like that. All right, so what else would you like to work on?
Number 4.
See what number 4. Oh yeah, number 4. I love these. You think I'm crazy, but I love doing Hess's law questions because it's, I don't know, it's like doing a puzzle. I'm not great at puzzles, but you know, these kind of puzzles I can understand. So when you have a Hess's law question, remember we just did at the end of last night, so it may not be stuck in your brain yet. But Hess's law says that basically I can take any chemical reactions and I can just add them all together and then basically subtract whatever is a product and a reactant. I can cancel those out. And whatever reaction I'm left with, I can just add all of those heats together and calculate the heat of the reaction that's left. So I can take like 10 reactions, add them all together, cancel out all of the reactants and products that are the same on each side, and just add all the heats. But if I do that, a lot of the times I'm going to have to change these reactions. Like for instance, if I multiply this whole reaction by 2, then I'd have 2 carbons plus 2 moles of oxygen, give me 2 moles of CO2, and I'd have twice as much heat released. I could also divide it by 2. So I'd have half a mole of carbon and half a mole of oxygen makes half a mole of CO2 and half as much energy is released. Or I can even flip it around so that CO2 goes back to the original carbon plus oxygen, just reverse the whole thing. But then it goes from being an exothermic reaction to being an endothermic reaction that takes energy put into it for that to happen. And how much? Exactly the same amount, but the sign is reversed. So whatever you do in these sort of problems, the first thing you want to do is find out where are my products and where are my reactants. If my reactants are on the same side, I'll probably just leave that equation alone. I might have to multiply it or divide it to get the numbers right, but I leave it in the order it is. But if I see that I have a reactant, but it's on a product side, then I've got to switch that reaction. So let's see how we would do that. So our reaction is up here. So this is the one we want to finish with. So we've got carbon as a reactant, I've got water as a reactant, and I've got carbon monoxide as a product and hydrogen as a product. So as I look through, so now I'm just going to start looking for carbon as a reactant. Where am I going to find carbon as a reactant?
Equation 1.
Yeah, equation 1. So that looks good. So I'm just going to leave out the states for right now, although it's a bad idea to do that because sometimes one of the reactions will be like, for instance, one of the reactions might be water to gas, liquid to gas. That takes heat for that to happen. And so watch for the state. The state may be very, very important. Here we're dealing with everything as a gas except for carbon, so I think we're okay. But in other ones we look at, one of our reactants might be water as a liquid, and we look at the reactions, and one of them has water as a gas as a reactant, so we'd have to make sure we get that right. So we've got carbon plus oxygen gives us CO2, and our delta H is minus 605. Okay, so far so good. So water as a reactant, where are we going to find that? Where are we going to find water, basically? Let's just look for water. Water is a gas.
Number 3.
That's number 3. Yeah, so that's going to be in number 3. 2 problems. It's water here is a reactant, is a product. So I'm going to flip that around. So I'm going to flip it around, and it looks like I should probably divide that by 2 because I only want 1 mole of water. So I'm going to change this one. I'm going to go water gives us H2 plus half a mole of O2. So what do I do with the delta H?
Change it to a plus.
Yep, change it to a plus, and what else?
Divided by
Because I've switched it and I've divided it by
By
1/2. Yeah, so I need to switch it and divide it by, or multiply it by 1/2. So 638 divided by 2. So that's going to be plus 319. Okay, so now I've got my 2 reactants. Now products, I want carbon monoxide as a product. Where am I going to find carbon monoxide?
Number 2.
Number 2. So there's my carbon monoxide. But again, I got an issue because there's 2 moles of carbon monoxide and I only want 1. So I'm going to flip that one as well and divide it and multiply it by 1/2. So let's do that, see what we get. So this time I'm going to have CO2. Just 1 mole of CO2 gives me just 1 mole of CO plus half a mole of O2. And what's going to be my delta H this time?
966.
Nope.
Negative 966.
Nope.
483.
There you go. Yeah, because we're changing the sign because I flipped the reaction. So now it's a plus. But I also multiplied it by 1/2. So it's going to be half of that. So it's going to be plus 483.
Can you tell me why you multiply by half?
Because in the original reaction, I only have 1 mole of carbon monoxide. And in reaction 2, there is 2 moles of carbon monoxide. I only want 1. So I need to change that twice. I need to flip reaction 2 around so that carbon monoxide is now a product rather than a reactant. So the sign changes, and I have to multiply it by 1/2 because I only want half of that amount of carbon monoxide. I don't want 2 moles, I just want 1. So I change it so that there's only 1 mole of carbon monoxide now, where there used to be 2. Okay? So basically now I'm going to see if I have everything right. So basically now I'm going to add everything together. So when you add everything together, you add everything that's on the reactant side, and then you add everything that's on the product side together. So let's do that. So I have carbon and oxygen and water and carbon dioxide as a reactant. These are my reactants. And these are my products. So before I start adding things, just to make my life easier, I'll see what I have on both sides and then I can cancel those, okay? So I've got oxygen on both sides. So how many moles of oxygen do I have on the reactant side, on the left side? 1. I just got this 1. So there's my 1 mole of oxygen on the reactant side. How many moles of oxygen do I have on a product side?
1.
1. Yeah, I got half here, and I got half there. So I have 1 mole of oxygen as a product and 1 mole as a reactant. So I can cancel those. So that gets rid of my oxygen. It's being produced and it's being consumed. So I have the same amount of oxygen at the beginning as I have at the end. So basically it does not, and we'll talk about this later tonight. It's like energetically, it's like it was never there, because all the energy I put into creating it, that same amount of energy was used in consuming it. So energetically, it was like it was never present. The net effect of that oxygen is 0, because the same amount of energy goes into making it and breaking it. So I can eliminate it. What else can I eliminate? I have something else that's on.
Carbon dioxide. Carbon dioxide.
That's right, yeah. I have carbon dioxide on both sides. How much do I have on both sides?
1.
1 of each.
Yeah, I've got 1 mole here, and I've on the reaction 2 gave me carbon dioxide as a reactant, and reaction 1 gave me carbon dioxide as a product over here. So I basically can eliminate that also. So what else can I eliminate? That's basically it, right? So now I add everything that's left over together. And when I add what's left over, on the reactant side, I have carbon plus water makes what's left on the product side.
OH.
Carbon monoxide plus H2. And that is the reaction we were looking for. That is the target reaction.
How about OH?
There is no OH.
In the first product, CO2 and OH?
First product, CO2. There isn't any OH.
I think that's a delta. I think that's
Okay, sorry.
Oh, yeah. So yeah, sorry about that.
Okay, another question. You said we have another question. You said we have 1 mole of oxygen in the reactant, correct?
Mm-hmm.
Then in the product, there is 1 in the second one and third one. How you cancel 1 in reactant?
Because they add up to the same. I have a total of 1 mole of oxygen on the reactant side. That's from.
Yeah, but in the product, we have
Also have 1.
1. Yeah, half, correct. Okay.
Yeah, also have 1. So then, to figure out how much energy it actually takes to do that target reaction, all we need to do is just add these numbers, these 3. And that's why it's really important to get the sign right, and to get the, if you're dividing or if you're multiplying, get that right. But the sign especially, because that'll throw you off. So we just take minus 605 plus 319 plus 483. So our final number is plus, and it's important to have the plus there, 197 kilojoules. So that would be the molar reaction enthalpy for this reaction, plus 197. So would that be an endothermic or an exothermic reaction?
Endothermic.
Endothermic, right? You have to add energy to make this go. Yeah, so you can see that we had at the beginning we had 3 exothermic reactions, and we combined them and moved them around, manipulated them. So at the end, we had one endothermic reaction. Shall we do the other one as well? I'll have you help me a little more with the other one. Let's do the other one as well. So the other one is
Can we
6.
do number 7? Okay. Let's do 6 and 7.
Yeah, you have to do 6 first.
Okay.
You can't do 7 without doing 6 first. So this is the same sort of question, but in this one you actually have to figure out what delta H combustion means. What do you think that means?
It's C plus O2,
Mm-hmm.
and then it makes CO2.
Right, exactly. So just combustion just means you're burning it in the presence of oxygen. So this reaction would be, oops, let's make these a little smaller. So C plus O2 makes CO2. So combustion of hydrogen would be what?
H plus O2 makes H2O.
No, not H2, not H. What's the most stable form of hydrogen?
H2
Yes, the H2
plus
plus
O2.
O2 gives water. But since we're dealing with delta H combustion means the combustion of 1 mole. So this would have to be a half mole of oxygen because we're dealing with 1 mole of hydrogen. So 1 mole of hydrogen plus 1/2 mole of oxygen makes 1 mole of water. And then the last one, so this one's minus 394. This one's minus 242. And the last one is methane. What's methane? You want to remember what methane is?
CH4?
CH4, right. So 1 mole of methane. And that gives you, remember, that gives you CO2 and water. So 1 mole of methane, that would give you 1 mole of CO2 and 2 moles of water. And the amount of oxygen that would require would be 2. Right? Because we have 2 here and 2 there. So yeah, that's balanced. So these are our 3 reactions. And this one's minus 891. So basically we have to take these 3 reactions and figure out how we wind up with this. So first, look for carbon as a reactant. So what reaction is that?
The first one.
That's the first one. Right, so let me change the color. That's the first one. So that's, oh, god damn it. That is C plus O2 gives you CO2 and minus 394. Right, next. Now I want 2 moles of hydrogen as a reactant.
It's the second one, but you have to multiply it by 2.
That's right. That's right. So that's going to be number 2. So that's going to be 2 H2 plus O2 makes 2 waters. So what's going to be the delta H for that one?
Negative 484
Yeah.
kJ.
Yep, we just multiply it by 2. Because it's twice as much. Now, CH4, we want that as a product. So where are we going to get that?
It's the last one, but you have to switch
Last
it.
one. Yeah, it's this one. So what do we have to do to it?
You have to switch it to,
We have to invert it. Okay.
okay.
So that one would be then CO2 plus 2 waters makes CH4 plus 2O2. What's the energy associated with that one?
Say
It's the same number, but
Positive 891.
yeah, but a different sign. Exactly. So remember, when we burn something, we release energy. And this is basically the opposite of that. I'm going the opposite way. I'm creating methane. That takes energy to do that. It's easy to blow it up, and it releases a lot of energy. Now I'm making it. That takes energy to do. So instead of minus 891, it's plus 891. Excuse me.
because it's
Now we can start seeing if we have all the right amounts that we've been looking for. So 1 carbon, 2 hydrogens on the left, that looks good, and 1 CH4 on the right. So I think we got our amounts right. Now we can start canceling things that are on both sides. So what are on both sides that we can cancel?
The 2H2O.
Yeah, there's 2 waters on both sides, right? So I've got water as a product in my second reaction there, and I've got 2 moles of water as a reactant in the third one. So exactly the same amount. So I can cross them out. Now, I just want to point something out here. If there were 3 moles of water as products and only 2 moles of water as reactants, I would eliminate the reactants and then leave the 1 mole of water left over on the product side. Because when we're calculating energies, basically the net amount of energy involved as far as water goes is into making 1 mole of water as a product. So I have to have that. But in this instance, it's exactly the same amount, so I can just cross them out entirely. So what else do I have as both products and reactants?
CO2.
CO2.
Yeah, I've got oxygen on both sides. So what's the total amount of oxygen I have as reactants?
2.
2. Yeah, I got one here and I got 1 there. And as products?
2.
2. So what can I do with all my oxygens?
Cross them out.
Yeah, same amount. I can just get rid of them. Anything else?
CO2.
Yeah, I've got carbon dioxide on both sides. How much?
One.
Yeah, I've got 1 mole as a reactant in number 3, and I've got 1 mole of CO2 as a product in reaction 1. So what can I do with my CO2s?
Cross out.
Yeah. So you see, all I've got left now,
CH4.
1 mole of carbon plus 2 moles of hydrogen gas give me 1 mole of methane. And that is precisely what I was looking for. Of course, you don't need the 1. That was just kind of stupid. Just for emphasis. So, and there's nothing else left over. Everything else has been eliminated. So that's, I said, one thing I like about these questions is that basically, you've got it right if you wind up with this. The only thing you have to worry about then is, did I do the right thing with my signs and my multiplications? So we didn't multiply anything, right? We just switched signs. So, oh, actually, no, that's not true. We multiplied the second one. So just want to make sure. So the first one we didn't do anything to. So the numbers are the same. The second one, we multiplied it by 2. So it should have the same sign, be twice as much. And yes, that's true. And the third one, we just switched it. We didn't multiply it by anything. So instead of minus 891, it should be plus 891. So I think we're good. So now we just add everything together. What's our final answer for delta H formation of methane?
13 kg.
What is it?
13 kg.
13 plus or minus?
Plus 13 kg.
Plus 13. So is this a endo or exothermic reaction?
Endothermic.
Endothermic, but not by much. Doesn't take a whole lot of energy for this to happen. So generally, you just get methane from directly from natural gas. But if you actually had to make some, it wouldn't be that difficult. Just flow some hydrogen over powdered carbon at a little high temperature, and you're good to go. So, any questions about this particular one?
Professor, just I have to clarify for myself. How you change negative negative 891 to plus 891?
Because we switched the reaction around. The original reaction was the combustion. The original reaction was the combustion of methane. So it's methane plus oxygen making combustion products, CO2 and water. But on the bottom here, we switched it. We actually turned it around. We're actually creating methane this time. And so since it's the opposite, the sign of the heat has to be opposite. So it went from being an exothermic reaction where methane is burned to being an endothermic reaction where methane is produced. So we have to switch the sign.
Okay, got you. Thank you.
Yeah, no problem. Right, we got time for a couple more. Is everyone clear on that one? It just takes practice with these. It just takes practice. Go check the, there's tons of online Tessa's Law questions to practice with. And there's a bunch of them in the textbook. There's a whole bunch. Now, believe me, if you go online, there's just like thousands and thousands of these.
And now we don't need to count the temperature together to see how much left. Like we don't need to say 300.
Temperature?
Yeah, the heat, I mean.
The heat is the heat of formation would be plus 13 when we added minus 394, minus 494, and plus 891. We added them all together. So the delta H for this reaction, which is what we solve for, is plus 13 kilojoules. Yeah, I just need to write just a couple more things on this page to make it a little more confusing. All right, so anything else we want to try?
Can we do number 7?
Sure. Okay, perfect. So we need the answer to number 6 for that. And the answer to number 6 was delta H formation. So HF, that stands for delta H formation. I'm going to be talking about that tonight. That basically is what it says. That's the amount of energy required to form something. So delta H formation for methane was plus 13 kilojoules. So if 500 kilojoules of energy is absorbed during the formation of methane, as we did before, what's the volume of gas produced? So this turns from a thermodynamics question to a gas law question. So to figure out the number, so this is 1 mole of methane is equivalent to 13 kilojoules, right? This is the equivalence we're dealing with. So if 500 kilojoules were absorbed, so absorbed meaning it's an endothermic reaction, right? That energy is absorbed. So for 1 mole, it takes 13 kilojoules of energy to absorb. It absorbed 500. So how many moles of methane is that?
.46.
Yep. So that's 38.46 moles of methane. Now it's just a gas law problem. So now we have our N. N equals 38.46 moles. So basically all we did to figure out the number of moles is to treat this as a reactant. So my reactant to making methane is 13. I need 13 of these things. I need 13 of these things called kilojoules. Well, if I put 500 of them in there, that's how many moles of methane I get out. So we use the thermochemistry to figure out the number of moles. And now we're just going to use the gas law to figure out the volume. Hopefully we remember what we're going to use for what's our gas law equation?
PV equals nRT.
PIV-NERT. Good old PIV-NERT. Yes. We're going to be using PIV-NERT. And so we have solved for N. So N is 38.46. What is my, let's figure out the rest of it. What is my temperature?
100.
Yeah, my temperature is 100 degrees C.
So I need to
what's
switch
what's my temperature in Kelvin?
273.15 or
Plus 100. 273.15 is at 0. That's the temperature in Kelvin when you have 0 degrees Celsius. I have 100.
73.15.
Yeah, so it's 373.15 Kelvin. And what's my pressure?
10.0 ATM.
Yeah. So I don't have to do anything to this because remember, we usually deal with atmospheres, liters, Kelvin, and moles. So right now I've got my moles, I got my Kelvin, I got my atmospheres. So I'm pretty much good to go. So I want to solve for V. So what
I think just
form?
the R.
Oh yeah, well R we just look up. R is, well, let's set up our equation first. I want to solve for volume. So how am I going to set up my gas law equation?
move B on the other side, divide the other side by pressure.
Right, divide both sides by P. So then I'll wind up with V equals N, which is 38.46 moles. R, anyone remember? 0.0821. Everyone remember the units?
It's too long.
Moles liters over ADM K. How do we
It's mole liters? No, I don't think that's. What are the units again?
ATM liter divided
Atmosphere
by
liters, yeah, over moles Kelvin. And then we multiply that by 373.15 K. And then divide the whole thing by 10 atmospheres. Right, so I have atmospheres in the denominator, and I have atmospheres in the numerator of the numerator, so I can eliminate those. I've got Kelvin in the numerator, and I have Kelvin in the denominator of the numerator, so I can eliminate those. I've got moles in the numerator and moles in the denominator in the numerator. So what I'm left with is liters. So basically, I'm multiplying this number by this number by this number and dividing by this number. And I'm left with liters, which is what I want. So 38.46 times 0.0821 times 373.15 divided by 10. That's a lot. So what do people get?
117.8245 liters.
117.825. Yep, that's what I got too.
8245.
8245. Okay, fine. You want to be like that. All right, yeah,
Liters.
liters. So how many significant digits can I use?
2.
Yeah, you're pretty much stuck with 2 because all we solved for, remember, we were stuck with 13 kilojoules per mole. If we had 13.0 kilojoules per mole, we could have used 3 significant digits, but we only have 2. So if we want to take that number and round it to 2 significant digits, what's our answer?
120 liters.
Yep, exactly. So our final answer would be 120 liters.
The answer is 120.
Mm-hmm.
So is that okay to change? I mean, like,
We only have 2 significant digits we can work with. So
because
kinda
usually when we round number, we round it if it's after those one, but this is before.
yeah, we only have 2 significant digits. So basically we're just stuck with these 2. So the 1 we leave alone. And then the second one, well, we have to decide whether we leave it as a 1 or change it to a 2. And since it's followed by a 7, we round up. So 120. We round that 11 to a 12. Yeah, you got to do that kind of rounding all the time. It's not always after the decimal. Sometimes it's before. Because basically it means when I have only 2 significant digits and 3 numbers, it tells me like what's the closest in tens is my answer. If I have my answer in hundreds, it's 100ths, but how many tens are there? Well, 2 of them is the closest. 17 is closer to 20. All right, any other questions?
Can we do 5?
Number 2.
I'll make you guys do 5. How about that? Let's see
Can
what
you help
5.
us start with 5 and then go over to
Oh, well, yeah, we need 4. What was our answer to 4? Now I can't remember. Anyone write it down?
197 kJ.
Sorry, I can't hear you.
Positive 197 kJ.
Okay, kilojoules. Use the nomenclature. Oops, clear that. So go to the next one. All right, so our previous answer was plus 187. You said
97.
Plus 197.
Yes.
Kilojoules per mole. Okay. So if the previous reaction was performed at 25 degrees, and that's the amount of pressure, in a volume of 250. Okay. So actually we don't even need to know what the, it doesn't ask about the energy. It just basically asks you what the reaction was. So what was the balanced equation for the previous one? Just go back. It's
Carbon
so it's
plus
carbon
H2O.
plus water gives you 1 mole of carbon monoxide plus hydrogen. So C plus water gives you H2 and CO, right? Is that what we're looking for? Yeah. Okay, so we have an excess of graphite. And graphite is a solid, so it's not going to contribute to the pressure. So basically we're looking to see, this is just another Pivnert question, giving you a temperature and a pressure and a volume and asking you how many moles of water vapor do you have. So remember, that's a gas, that's a gas, that's a gas. So basically all you're doing is figuring out what is in water. So how do we do that?
We
It's
convert
based,
the
oh, go
temperature
ahead.
to Kelvin.
Right, so I'm just going to use the gas law. I'm just going to use Pivnert. And I need to solve for N. So I'll take my, right, so you take your temperature. What's my temperature going to be?
225 plus
So it's 25,
298.15 Kelvin.
298, right? 0.15. So it's 273 plus 25. So that's my temperature. And what's my pressure? Now it's given in torr. So now I have to convert torr to atmosphere. How do I do that?
divide by 760.
Right. I multiply by 1 over 760. Right. So I got 749 torr times 1 atmosphere divided by 760 torr. So how many atmospheres do I have?
0.9855 atmosphere.
0.9855 atmospheres. Okay. So I've got my temperature, got my pressure. What else do I need? Oh, volume. Oh, also, what's my volume?
2.50 liter.
Right. 2.50 liters. So now basically I just plug them in to my Pivnert. But since I want to solve for N, how am I going to rearrange my gas law?
Divide R2 to PV.
Yeah. So just divide both sides by RT. And I've got N, actually, yeah, N equals PV divided by RT. Let's just plug those in then. All right, so N is going to be equal to my pressure, which is 0.9855 atmospheres times our volume, and that is 2.5 liters. And I'm going to be dividing that by R. And what are my units for R?
Times Kelvin, ATM times K divided by mole over liter.
Atmosphere liters over mole Kelvin, right? And then I multiply that by my temperature. So multiply that by 298.15 K. All right, so got atmospheres on the top, atmospheres on the bottom, liters on the top, liters on the bottom. And I've got, and in the denominator, I've got Kelvin as a numerator and Kelvin as a denominator. So I'm left with moles. So that's what I want. I want to be left with moles. And it's in the denominator, it's 1 over moles. So I'm left with, when I flip it over, I get moles. So how many moles of water vapor is that?
0.10065.
0.1 65 moles. So that's how much water vapor is there. Oh, gas. So you go back to the balanced equation we had, which was carbon plus water makes H2 and carbon monoxide. What's the molar ratio of the water vapor to hydrogen and carbon monoxide?
1 to 1.
1 to 1. So same amount. So that'd be your answer right there. So what would be our number of significant digits?
2.
2? You sure?
Sorry, 3.
3, right. There's 3 digits, 3 in the temperature, there's 3 in the pressure, and there's 3 in the volume. So if I want to round that to 3 significant digits, what's my final answer?
The volume is
0.101.
2.5, correct? Like 2 significant.
3.
In volume 2.50, we do not count 0, correct?
Yes, we do, because it's past the decimal place. If it's past the decimal place, it means it's there for a reason. It means we measured exactly 2.50 liters. So when we round 1.0065 to 3 significant digits, we get 0.101 moles. Yeah, so trailing zeros, when it's on the left side of the decimal, are not significant because they're just placeholders to tell you how big your number is. So it's 10, it's 100, it's 1,000, it's 10,000, etc. But when it's past the decimal place, it means it's there for a reason. It means I can measure that. It's not 2.501 and it's not 2.499. It's exactly 2.50. That's the meaning of the 0 past the decimal place. It's an indication of precision. Okay, is everyone confused enough now?
Question. Can you
Sure.
help us give help us start number 2 with the heat capacity being in the
Oh,
calorimeter?
sure. Let's have a look at it. All right, yeah. So basically here you just set up Q as we always do. So basically I've got Q of my mineral minus Q of my mineral equals Q of the water. It's always going to be this. Your Q of your negative Q of the unknown equals Q of the water. But difference being there's two, the heat is going to two places. It's going into the water and it's going into the calorimeter. So it's also equal to plus Q calorimeter. So if we did this in the lab, you would have to have both, because we can't design such a perfect calorimeter that it's, you know, its heat capacity is 0. It's going to be something. And so in this instance, and also notice there's no mass units there. And the reason for that is basically when you fill up your coffee cup or whatever it is with water, the mass of the calorimeter is basically meaningless. Where the heat gets lost is in the area of the sides of the calorimeter. It has nothing to do with the mass of it. It has to do with the surface area of the calorimeter. So basically what you do is you fill up the calorimeter to the same place every time and just figure out how much heat gets lost. And then you just give it in joules per degree. So then you just plug in everything else you need to know. Figure out, based on the change, how much heat went into the water. Then you just use the heat capacity of the water times the mass of the water times delta T. And do the same thing with Q calorimeter. What's the heat capacity of the calorimeter? Well, it's 15.7 joules per Kelvin times delta T. And you just add these two together. Add this one plus this one, add them together, and that's going to equal Q of the mineral, okay? It's just one more step. It's exactly the same as the other questions, but just one more step in it. There's a little bit of heat that goes into the calorimeter, and we have to account for that. So if you take the heat that was lost into the water plus the heat that was lost into the calorimeter, all that heat came from the mineral that was heated up. So just add the two together. Add the water and the calorimeter heat that was gained together, and that will equal the heat that was lost by the mineral. And then it's just solving for the heat capacity.
So I have a question.
Mm-hmm.
Is it do we use the final temperature in the calorimeter?
Yes.
Find the
Yeah,
difference?
the final temperature is the same for everybody. It's the same for the mineral, the water, and the calorimeter. So, so the initial temperature of the water is going to be same as the initial temperature of the calorimeter, right? So the calorimeter delta T and the water delta T are going to be exactly the same. They're going to be 32.4 minus 23.6. So they're going to be around 9 degrees. So the delta T here will be like plus 9 degrees, and the delta T here will be plus 9 degrees. And the delta T for the mineral will be 32.4 minus 98.7. So that'll be negative. Okay? Yeah, you just have to account for that little bit of heat that sinks into the walls of the calorimeter. So as the water heats up, the water has some amount of surface that it shares with the calorimeter, and a little bit of heat goes from the water into the calorimeter, and we need to measure that as well. So are you wondering why there's no mass to it? Is that a confusing thing?
Oh no, I figured it out.
Okay, good. Yeah, because basically if we made a 1 pound calorimeter and put 100 mils of water in it, and we made a 17-ton calorimeter and put 100 mils of water in it, the heat capacity of them would be the same, because it's only how much water is exposed to the calorimeter. It doesn't really have anything to do with the mass of the calorimeter. All right, cool. Any other things before we go? We're gonna get to some interesting problems in lecture tonight. hopefully it'll make the whole thing make a little more sense. We're talking about bonds breaking and bonds forming, and another way we can calculate heats of reaction. All right. So anything else? You good to go?
Yes.
All right. Good. Yeah, and the computer didn't melt down once, so pretty happy about that. We'll see how that goes. I just need to switch some programs over, and I think I'll got it. So right now, I have no idea where this particular recording is going. So hopefully, I'll be able to find it.
Professor, I have a question for the exam. The one will be on Friday. Could you
Yeah.
please clarify, like, which recitation will be in the exam, which chapter?
Yeah, all the ones since the last test. So whatever the last recitation was. So we're up to this one. So I don't know the number exactly. I'll look it
No,
up.
from recitation number 7. But the recitation that we're gonna take on Thursday, it will be included in the exam?
Yes, because it'll be on thermochemistry.
But, like if we
So
have,
it's 1 through 9 for lecture.
I'm sorry?
What number recitation you said?
Yeah, 4 to 9. 4, 5, and 9. We just go right from 5 to 9? Yes, I think we did.
so the pressure, it will not be in the exam?
Pressure?
Mhm.
No, gas laws. Oh, I'm sorry. Yes, 8 and 9. Duh. Yes. So,
So,
yeah. So shapes, gas laws, thermochemistry.
so it's about 4 chapters or 3?
4.
Can you take one chapter out and put it in the final? I feel like it's too much for Friday.
Yeah, I mean, the questions, well, yeah, I mean, the questions on thermo won't be dealing with it won't be dealing with the ones, the recitation on Thursday. It will be on this one. So
Okay.
we'll
Yeah.
have to know calorimetry, and we'll have to know Hess's law.
Yeah.
But then that's it.
Okay.
Yeah.
So what we did today is going to be on Friday. Is that what
Yes.
you're saying?
Yes. Oh, on the final, definitely. But yeah, but on this test also. Yeah.
Okay. So it's shapes, gas law, and thermochemistry.
Yeah, the first part of thermochemistry. Yep. Yeah, so Lewis structures and shapes, gas laws, and thermo. First part of thermo. There's something new we're going to learn tonight that won't be included, but it will be on the final.
Yeah. Okay.
All right. All right. We'll see you tonight. Hopefully, if I figure all this computer's nonsense out. All right. We'll talk to you soon.
Thank you, Professor.
All right. Thank you guys. Stay well.